Welcome to lecture number 37 of the Statistical Thermodynamics for Engineers. So we already started looking at, how we go from particles to an assembly. Okay. So the idea is that, we have seen quantum mechanics, we have seen spectroscopy, and this has led to relationships which gives you the energy and the degeneracies for all the four energy modes, which are basically translation, rotation, vibration, and electronic. Okay, so we have also shown that if there is mode independence, okay, then diatomic molecules mandates something called a simplex model, which assumes a combined rigid rotor and a harmonic oscillator. Okay, and we have spent plenty of time actually, showing that thing. And the table 8.1 from the book, which we just showed here, okay, around here, we showed that the translational energy can be converted to the wave number units, and thus defining a term called alpha TR. Okay, and we also realize that translational energy is unique because it depends on the assembly volume. Okay, no other energy mode is affected by the assembly volume. That means the macroscopic properties defining the particle assembly. Moreover, the degeneracy of a translational mode requires representation through a probability distribution function, which we already did previously. Now we have also seen for the internal modes, okay, we require a rotational constant B for the rigid rotor and vibrational frequency omega E for the harmonic oscillator, both of which can be determined from the spectroscopic measurements that we covered in the previous lectures. Okay, so what it does is that it provides tabulations for the electronic energies of atoms and molecules, and for atoms, the required degeneracy is evaluated by summing over the multiplet caused by the different J values, whereas for the molecules, we have what is caused by spin splitting, okay, in this particular case. Okay, so this we already have done, and we have already a fairly good idea. Now that we know how the energy levels and the degeneracies correspond to the translational, rotational, and vibrational energy modes of an independent particle assembly. Now we are going to use this particular knowledge, okay, to proceed towards a macroscopic description of assemblies of atoms and molecules, and that is exactly what we started to do over here. But as we said earlier, let us convert all of these in terms of the unit of temperature, right? So let us write the temperatures once again. Okay. So for example, theta T, which is translational temperature, is Hc by K into alpha TR. And this is roughly of the order of 10 to the power of minus 16 K. Then of course, theta rotation, which is written as theta R, is approximately 10 K, and that is equal to Hc by K into Ve. And then you have the theta vibration, which is equal to Hc by K into omega E, which is also more or less 10 to the power of 3 K. And then, of course, we have the electronic mode, which is Hc by K into Te, which is 10 to the power of 5K. So what we see over here is that these two temperatures, the translational and the rotational modes, are fully operative. They are fully operative, okay, even at room temperatures. Actually below room temperatures, to be precise, even at room temperature. Okay, they are completely accessible. Okay, and this is, of course, all these values are for say molecular hydrogen. Okay, so they are activated at room temperature or below room temperature, at or below room temperature. Okay, while on the other hand, the other energy modes are 10K and 10 to the power of 3K and 10 to the power of 5K, 10 to the power of 3 and 10 to the power of 5. So we find that the vibrational and the electronic modes, those are the vibrational and electronic modes are operational, okay, only at temperatures considerably operational at temperature greater than 300K or much greater than 300K. Okay, so this observation is very important because we can now use this for the prediction of the thermodynamic properties. So you now know which temperature, which mode is activated when or at what temperature, so to say. Okay, now what did we assume? We assumed, just to do a recap, we assumed that there was a separation of energy modes, right? Okay. So separation of energy modes or full separation of energy modes. We first separated the external mode from the internal, 3 internal modes, okay, by converting to a coordinate system, remember, where all translational motion with respect to the molecule center of mass. In this way, any interparticle motion could be expressed relative to the center of mass. So therefore, the Schrodinger's wave equation could be separated into 2 equations, one controlling the external and one controlling the internal motion of the particles. Okay, so therefore we would write that external into internal. Okay, energy was of course internal plus external, right? And G, which is the degeneracy, is external into internal. Okay, these were all independent of each other, right? Okay, so we converted this by considering a coordinate system, okay, using the molecule's center of mass in this particular case, right? And we considered a full separation of the energy. So then we did what? We did the Born-Oppenheimer. Next, we did the Born-Oppenheimer approximation. Okay, approximation. And we found the Morse potential describing any electronic state could be fashioned by solving the Schrodinger's wave equation. Okay, so the predicted electronic energies defining the Morse potential, okay, assumed that there is a continuum of stationary internuclear distances. Okay, so this internuclear potential, okay, was the primary input that was needed when you were solving the Schrodinger's wave equation for the combined rotational and vibrational motion, right? So we have also, what we did was that the internal part was further divided into electronic and rho vibrational, and the internal energy was divided into electronic plus rho vibrational, and G internal, which is basically the degeneracy, was given as electronic into GRV. Okay, so we uncoupled, finally what we did was that we uncoupled the vibrational and the rotational mode, uncoupled vibrational and rotational modes using 2 approximations. One is the rigid rotor, right, and the other one is a harmonic oscillator. These were the 2 modes that we used to separate. Okay, so these were the 2 approximations that we used to separate. So what we did was that now they could be written, Schrodinger's wave equation could now be written in terms of independent potential functions for both the rigid rotor and the harmonic oscillator. Okay, so they produced independent energies and degeneracies. So the rho vibrational was further divided into rotation and vibration, and ERV was further divided into rotation plus vibration, and the degeneracy RV was given as G rotation and G vibration. Okay, so accumulating all these approximations and assumptions, we find that the total energy is therefore translational plus rotational plus vibrational plus electronic, and G is equal to G translation, G rotation, G vibration, G electronic. Okay, so in other words, there is a full separation of the independent energy modes. So the total energy is simply the sum total of the individual component energies. The overall degeneracy is the product of the component degeneracies, as anticipated, because it was a probabilistic interpretation of the independent events, because these were independent events to begin with. Okay, so there were now three fundamental prescriptions. One was the Born-Oppenheimer approximation, which gives rise to the Morse potential. The second was a harmonic oscillator model, which works only for lower vibrational levels. That means it works, if you recall, this was the Morse potential, and it worked right around here. This was the zone. So it was essentially valid for the lower vibrational levels. And of course, then you had the rigid rotor assumption. Okay, so all these three assumptions or three prescriptions was what was needed to solve this particular problem. Okay, and so armed with this, now that we know that this is what it was, then we wrote the total energy, or the molecular internal energy, okay, in terms of the wave number. Internal is TE plus E plus half plus Fj. Okay, so the ground vibrational energy prescribes non-zero energy. Okay, so as we know already, so this energy level obviously represents the lowest possible molecular internal energy outside electronic or rotational contributions. Okay, so on this basis, this is useful. We find it convenient because when calculating thermodynamic properties, to place the zero of the energy at the lowest vibrational level within the ground electronic state. Okay, so that was what was important, and this is what we actually did. Okay, to evaluate directly the internal energy in an upper electronic state, we may define a revised electronic energy gap. Okay, so like this. So we write it like this: E naught E Fj. Okay, so where we have, in this expression, we have dispensed the ground vibrational energy in the upper electronic state, as this 0-point energy is immaterial given the definition of T naught. So what is the definition of T naught? The definition of T naught is this. And let's draw a simple figure which will let you understand this. Okay, so this is E prime equal to 0. This is E double prime is equal to 0. Okay, and the difference between these two this is TE. Okay, and this is the first, and this is the first. Okay, so this is actually your T naught. Okay, so you understand that we brought in T naught. Okay, by the definition of T naught, we have eliminated the ground vibrational energy. Okay, so that's why the half is not there anymore. Okay. Okay, so employing this revised zero of energy, now by simply looking at this particular figure that we just now drew, this particular figure, okay, the various energy levels without their Morse potential can be shown in this particular way. Let's draw this diagram also. So this requires a little bit of an effort. Let's see if this can be drawn properly. This is V double prime equal to 0, V double prime equal to 1. This is V double prime equal to 2. Okay, and then you have an upper level. Okay, so this is V prime equal to 0, prime equal to 1, V prime equal to 2. Okay, so now put this. Okay. Then of course, so this is the X, this is the A, and yeah. Okay. So this is basically your T naught. All right. And then you look at the different transitions. Okay. When you look at the different transitions. Right. So this is the diagram. This is like an energy level diagram that we have drawn. Okay. And we have drawn the energy levels for both vibration and rotation within both the ground state and the first excited electronic state. So these are the corresponding rotational bands, and these are the vibrational ones. And this is A, this is the ground electronic state, this is the first excited electronic state. Okay, so so the revised electronic energy gap bridges this V double prime equal to 0 to V prime equal to 0, the vibrational vibronic levels. Okay, which is also shown in this particular figure. Okay, the T naught is well marked over here. The vibrational energy gap is invariant for the harmonic oscillator, but actually decreases at higher energy levels for the anharmonicity, which we know we brought in through the complex model, right? In contrast, the rotational energy gap always rises with increasing rotational quantum numbers, right? Okay, so we also know that the vibrational energy gap, which is delta EV vibration, okay, is invariant. It's invariant for harmonic oscillator. But actually decreases higher vibrational levels for an harmonic oscillator. In contrast, the delta E rot, which is basically the rotational energy gap, this always rises, okay, with increasing rotational quantum number. Increasing rotational quantum numbers. Okay, rotational quantum numbers. Okay, and so we can provide different transitions. For example, we can provide a transition which is, say, R equal to 1, which is basically, let me mark it with blue so that you can see this particular. This is, for example, R1. This is one sample transition. Okay, and we also note here, that delta E rotation is greater than delta E vibration, and this is definitely less than delta E electronic. In other words, the energy gap for a vibrational mode is less than that for the electronic mode, but greater than the rotational mode. This result, of course, is consistent with the characteristics temperatures. So the vibrational modes, the energy gap, this energy gap is much more than this, and this is much more than that. Okay. So the separation now that you know that these can be separated, okay, and separation of energy modes now also will play an important role in the evaluation of the macroscopic properties now. So all thermodynamics, if we take the dilute limit, that all thermodynamic properties in the dilute limit are related to the natural logarithm of the partition function, as we already did. This is significant because it ultimately says that such properties can be evaluated by adding the separate contributions arising from each energy mode. Okay, for example, so just to write it very clearly, that all thermodynamic properties, just to reiterate, thermodynamic properties in the dilute limit, in the dilute limit, okay, are related, okay, to natural log of the partition function. Okay, the observation is very significant because now we know that it can be sum totaled. So if you recall that our z, which was the partition function, was written as j gj e to the power of minus ej by kt. If you recall, this now can be written as, because of the separation, gtr. So this is translation. This is the internal modes. Okay. This is translation k, internal mode L, exponential. All these are within the summation, obviously. Minus ETR k plus E internal L, okay, divided by KT is summed over K and L. So this one is, of course, here. All right. Okay. So that now Z can be written as summation K GTR K e to the power of translation K by KT, okay, multiplied by summation L G internal L e to the power of minus E internal L by KT. Okay, so this is equal to Z translation into Z internal. So you can see the partition function is itself like that, can be separated into two. Okay, so for all the four independent energy modes for any diatomic molecule, okay, we can write therefore Z as Z rotation, Z vibration, Z electronic. So the logarithm of Z converts all these into a summation. So this is ln Z translation plus ln Z rotation plus ln Z vibration, ln Z electronic. So the partition function is multiplicative, whereas the logarithm is, of course, additive. So all thermodynamic properties in the dilute limit can be expressed in terms of ln Z that we have seen already, right? So this implies that such properties are also additive therefore for the available energy modes, right? So if you recall, now if we write it, this is the internal energy part. This is T ln. So you can write it like this, therefore, B plus T. So this is ZTR, obviously. Okay, so this is rotation divided by B Of course, and T ln Z vibration B plus T ln Z electronic divided by delta T. So as you can see, so it is a sum total of the 4 such expressions. So if we know the individual quantities, okay, which we can know, right? The individual quantities are dependent on the energy level and the degeneracy. And we already said what the energy levels of the degeneracies are going to be. If you look at this particular table now, right? We already gave these numbers. We already said that what will be the energy, correct? Through spectroscopic means. And through this nice separation, we are able to therefore show that, you know, the internal energy, for example, here, okay, is a sum total of all these individual components coming out of the 4 independent energy nodes. So similar should be the case with entropy and a lot of other things. So as you can understand, we use quantum mechanics. Now we can evaluate the energy levels as well as the degeneracy. We use those degeneracy and energy level in computing the partition function, assuming a full separation of all the 4 energy nodes, and that enables us to calculate quantities, macro quantities like internal energy, which is shown right here. So this is brilliant. So this is how we link the microscopic world to the macroscopic world using this. So in the next class, we will see that how entropy and all the other quantities, okay, can be computed using this, okay, and how these contributions therefore can now go, go a long way in computing all the other quantities that we can think of, right? Enthalpy and all the other parameters. So we close the class here. In the next class, we will go and first see that how entropy can be written, for example, in terms of these individual components. So thank you and see you in the next class.